Number 8. The reaction between crystal violet, which is some sort of big organic molecule, and sodium hydroxide is as follows. It looks like some sort of synthesis reaction where they just get together. As the crystal violet is the only colored species in solution, a spectrophotometer calibrated to a specific wavelength can be used to determine its concentration over time. And then they gather this data. Now, one of the things that we should bring up here is they're giving you the molarity of this colored species. And this lab is traditionally done with a spectrophotometer called a colorimeter. And you remember a lot of times you cannot measure the concentration directly, you measure the absorbance. But the absorbance will directly relate to concentration. Now, this has nothing to do with the rest of the stuff, but we're going to stop here because it's about learning, and it's very likely that in the future they will not just give you the concentrations. So if they gave you the absorbance, like say they said the absorbance in the beginning was 0.25 or something like that, how could you get it to concentration? And the answer, remember, is Beer's law. Absorbance equals ELK, where this is the molar absorptivity, which is a constant that has to do with the compound. In other words, it would be specific to crystal violet. This is the path length, so how wide the cuvette is, and that's almost always 1 centimeter. And this is the concentration that you're trying to find here. So if you knew the absorbance, you could find the concentration. So a little reminder of Beer's law and how you typically would go from absorbance to concentration. All right, so let me erase some of this stuff. Since they already gave us concentration, we don't have to worry about that, but just be aware that it's out there. Okay, then let's see. So let's look at A. They say in A, what is the rate of disappearance for crystal violet from 60 to 120 seconds? So because crystal violet is a reactant, it will be going down in concentration, as we can see here. And so if we're going from 60 to 120 seconds, remember that the definition of rate is change in concentration over change in time. Well, that's not too bad to do. So we're going to have a change in concentration, which is going to be from 3.8 times 10 to the minus fifth to 2.6 times 10 to the minus fifth. I think that's what that says there. Now you remember, generally, actually I've got these backwards. We really should be doing final minus initial. But the one thing we know is no matter what happens here in the end, the sign is going to come out to be negative. So I'm not going to worry about it at the moment. And then we're going to have 60 minus 120, which is 60 seconds. Let me write that out just so that we can kind of see what's going on there. So 60 minus 120. It would be nice if I had actually reversed the two of them, but it doesn't make a difference. So our final answer is this. 2.0 times 10 to the minus 7th. And our units here are going to be, well, on top we had a change in molarity, and it was on bottom, so molarity up here, and seconds down there. So our units are molarity per second, and that is a good unit for rate. Let's see, and I was just going to check sig figs here. I think, we do have two. The time, though, the time is 120 or minus 60 gives you 60, and so we're only going to have one sig fig there, so I probably should get rid of that. It should be 2 times 10 to the minus 7th, and you would definitely want to rewrite it. So I think 1 sig fig would be appropriate there. All right, on to part 2. So in 2, they want to know if the solution was placed in a spectrophotometer 30 seconds after mixing instead of immediately after, how would this affect the calculated rate? And so here's my answer. The rate of disappearance would be lower since the data was collected at a later time interval. The reaction will have a slower rate over time. And you can see this if we did the change in rate here, but the change in rate there, you notice it slowed down a little bit. And so over time, what the graph is going to look like is the concentration is going to start really high, and it's going to drop and sort of go like that. So if we were looking at instead of going from, say, 0 to 60 seconds, if we were doing from 30 seconds to 60 seconds. You can see that the average, the tangent line there, the average rate is slower at a later interval than it is at an earlier interval. So in here it'd be much higher. So the rate definitely slows down over time, and we would see that if we were recording it at a later time. Another way to see that is the one we did has a difference in concentration of what it looks like 1.2, and at this later one it's not even 1, it's what is that, 0.8 or so? So you can see it slowing down over time. Alright, and here in part B I jumped the gun earlier and sort of taught you about Beer's law. They're doing it backwards. Look at that. Beer's law shows up here. Given the path length of the cuvette is 1, so that's what L is going to be in Beer's law, and the molar absorptivity of the solution is 26,000, that's that little funky E, what would be the absorbance reading on the spectrometer at 60 seconds? So let's write down Beer's law. Ooh, I'm so excited that we get to do this. So Beer's law is the absorbance equals the molar absorptivity, so that's molar absorptivity. I'm just going to abbreviate it there. That's the path length, and we know C is concentration and A is absorbance. Alright, so at 60 seconds we see that our concentration is that, so I'm going to put that in on the other side, and they want to know what our absorbance is. So there we go. I plugged in our molar absorptivity, our path length, and our concentration, and solve them for the absorbance. This is reasonable. Actually, absorbances tend to range from about 0 to 2 at the highest, so it's a reasonable number. And the other thing is they generally are unitless quantities. And obviously you don't need to write that. There's no unit at all. But we do need to think about sig figs. This had 2, and I want to make sure I wrote down the correct number. I did. This had 2, and this had 2. So I'm probably going to want to do 0.99 for my absorbance.